The examples that we have considered till now, we saw that the data at our disposal were the population variance covariance matrix, or for that matter the population correlation coefficient matrix, that is the variance covariance matrix of the standardized variables. But in most of the situations, in reality, what we will have at our disposal is basically the data matrix. We may have p variables with us, x1, x2 to xp, and we shall have n independent observations on each of these p variables. And from that data, from the scratch, we have to calculate the principal components, the sample principal components, to do a complete analysis. So, now we take up the computation of principal components from such given data matrix, that is from the given data on a multidimensional random vector. So, that is what we have with us now, that is computation of the principal components from a data matrix. We have at our disposal, say as we said, that we have p variables on which we have, on each of which we have n independent observations, and so we prepare the data matrix, say script x, which is of the dimension p by n, which means that we have the p random variables and n observations on each of these, and hence the elements are arranged in this way: x11 up to x1n, x21 to x2n, and the last row being xp1 to xpn. So, what we have is the first row is giving me the first random vector, the sample of that random vector of the first random variable, and n observations of the first random variable x1. These are the observations coming from that variable x1. So, these are x11 to x1n. The first subscript 1 is telling me about the random variable that we have at this stage, that is x1, and the second subscript 1 to n is telling me about the number of observations that I have on this variable. Similarly, in the second row I have the second data and n observations on that variable, and the pth row is giving me the information on the pth variable. If you consider the first column, it is you have all the values of all the variables x1, x2, xp at the first instance, at the first case, that is the second subscript here is 1, right. So, we have what we have is n independent observations, that we have arranged in this way from a p dimensional, that is how we have the first dimension of the data matrix, p dimensional population with say mean vector mu and variance matrix, variance covariance matrix sigma. From here, what we can have is the sample mean vector. So, let us say the sample mean vector is what we denote by x bar, and it is nothing but the elements, since x is p dimensional, the data vector. So, we have this also as p dimensional, and we have x1 to xp. Obviously, the first one x1 is giving me the sample mean of the first random variable, that is I have x1j, j from 1 to n, that is the first row, elements of the first row from the matrix. And similarly, I go down to the pth such random observations, j of them, j from 1 to n, take sum of these and divide by n to get xpj. So, ideally we should, these are not vectors, we have to write them. In fact, we have the mark, that is x1 to xp, and these are the sample means from each of the cases. So, we have an upper bar actually. These are all elements making up the p dimensional sample mean vector. Similarly, I will have the sample variance covariance matrix, say I have S, and this is 1 by n minus 1, and then the first row is nothing but x1j minus x1 bar square, and then I have the covariance between the first and the second. So, I will have to consider x1j minus x1 bar, x2j minus x2 bar, and similarly the last one is giving me x1j minus x1 bar with xpj minus xp bar, right. The 2 element is talking about the sample variance for the case of the second variable. So, that is x2j minus x2 bar square. All these summations are over j from 1 to n, and the last one in this row is x2j minus x2 bar with xpj minus xp bar, and the pth one, ppth one, or the last element down here is the variance corresponding to the pth variable, that is xpj minus xp bar whole square, right. So, this is the sample variance covariance matrix I have with divisor n minus 1, and from the sample data now our objective. So, we have this, we may either have the complete data or we may have concise data like the mean vector and the sample covariance matrix, variance covariance matrix, whatever. Now, from the sample data we our objective is to construct the principal components. We construct the uncorrelated linear combinations. Basically, these are our principal components of the measured characteristic that account for, that is the purpose that we have at the background, that account for as much of the sample variation as possible. So, this is the crux of the calculation of sample principal components as possible. And now we say, suppose our first principal component, suppose L1 transpose X is the first principal component or first principal component sample linear combination, first sample PC or first principal component sample linear combination, it is the same thing. And let us say that L1 transpose Xj is nothing but L11 with X1j up to, if I denote L1 transpose Xj in this manner, so this is L1 transpose Xj and this is L1 sum up to L1 P Xpj, and this is defined for all j from 1 to n, and then I have, in that case I can express the sample mean of this component as L1, well this is according to notation, this is Lx L1 transpose X bar, and this is nothing but 1 by n sum of L11 X1j up to L1p Xpj sum over j from 1 to n, and this are basically, if you see the way we have defined. So, these are nothing but L11 X1 bar up to this I can write here, because I have defined the sample mean in this way, and then last one is L1p Xp bar, and this is giving me this L1 transpose X bar. This is the notation that we have used, and the sample variance in that case is, you have L1 prime X1 minus, you have to consider the mean out of it. So, that is L1 prime X1 bar whole square up to L1 Xn minus L1 x bar, this whole square, and this is getting divided by the divisor n minus 1. Also equivalently I can express this L1 x1 bar minus L1 transpose x bar square as L1 transpose xj minus L1 transpose x bar, this is there, along with L1 transpose xj minus L1 transpose x bar transpose of this, and this is nothing but L1 transpose xj minus x bar xj minus x bar transpose with L. And so sample variance equivalently, since I have this here, therefore sample variance is also equal to, I can write another form of this, is equal to 1 by n minus 1 with, well, what I write for each of these terms now I have to consider, that is L1 transpose x1 x bar x1 minus x bar transpose L1 up to L1 transpose xn minus x bar xn minus x bar transpose with L1, and this gives me 1 by n minus 1 L1 transpose sum of such terms, that is xj minus x bar xj minus x bar transpose j from 1 to n, and I have one L1 here. So, this is actually giving me, by our definition of the sample variance covariance matrix, this is nothing but 1 by n minus 1 L1 transpose SL1. Similarly, I can have the sample covariance, similarly sample covariances say between, I have say L1 prime xj and L2 prime xj. This can be, all these pairs can be expressed as in the same manner L1 transpose SL2, right. So, in this way I can continue, and I can very well, what we have to do in fact is basically calculate the eigenvalues from the sample covariance matrix or the sample correlation matrix, and then calculate the obtain the associated orthonormal eigenvectors to obtain the principal components, the sample principal components, right. So, the major task here is to calculate the sample variance covariance matrix and obtain the eigenvalues. Now, let us take up an example from real life data. So, real data example, and we have calculation of sample principal components. From standardized data, because that is what you will encounter mostly in practical situation. Your variables will be from whole gamut, where they have different sorts of description, interpretation, different units. So, the best thing here will be to consider standardized variables, so that we calculate eigenvalues not from the sample variance covariance matrix, but from the sample correlation matrix. So, that is what we are going to do here. We are calculating sample principal components from standardized data, and the data in this example, these are the weekly rates of return from 5 stocks, okay. And these stocks are Allied Chemicals, DuPont, Union Carbide, Exxon and Texaco, Okay. So, these are listed in the NYSE, the New York Stock Exchange. So, these are listed on the NYSE, and the weekly rates of all these 5 stocks were determined for the period Jan 1975 through, with old data, but does not matter, through December 1976. So, we have daily data, and from here we have calculated the weekly rates. So, these are the weekly rates are defined as, the weekly rates are defined as, we have current Friday closing price minus previous Friday closing price. That is one example, just to tell you how the weekly rates are calculated from the daily data by the previous Friday closing price. And there are some finer issues, like these are adjusted for stock splits and dividends. We may not go to the detail of this, we just assume that we have this data at our disposal to calculate the sample principal components. Okay. So, this is how we have calculated the weekly rate from the daily returns of the 5 stocks, and then we have to calculate, we have, so we can see that we have a multivariate data. We basically have a 5-dimensional data, and number of observations is of course the number of weeks that we have in this period. So, it is a multidimensional data, and we are going to look into the sample calculation of principal sample components from here and give some interpretation to those principal components. Okay. So, now we see the observations. So, we have the observations in 100 successive weeks. Okay. So, that the period that we said it has 100 weeks. So, 100 successive weeks appear to be, now what we are doing here, we are sort of trying to justify our initial setup, that we say that we have n independent observations. Now, meaning to this setup, what we will say that for each day the stock returns are independent, these are independent observations, but across the stocks they are not independent. Okay. By which we mean that since these are playing in the same market, the returns over each of these stocks, they are sort of interrelated with each other. The price of one will influence the price of the other and so on, but over the period these are all independent observations. Okay. So, the observations in 100 successive weeks appear to be independently distributed but the rates of return across stocks are correlated, okay, for a fixed time point. Okay. So, then we have let x1, x2 to x5 denote observed weekly rates of return for the 5 stocks, that is Allied Chemicals, DuPont, etc., up to Texaco respectively. Then suppose we have this information at our disposal, the sample vector, the 5-dimensional sample vector is given to us, if not the full data. If the full data is given to us, we can easily calculate the sample mean for each of these stocks and then give you the sample mean vector. Okay. So, whatever be the situation, if the data is given to us, fine, we will have to calculate it, otherwise a sample mean vector as a whole may be given to us, and this is given by, it is a p dimensional vector, its values are, the elements are 0.0054, 0.0048, 0.0057 and 0.0037. This is our sample mean vector. And we have correlation coefficient matrix of these stocks. So, covariance matrix of the standardized variables, covariance matrix of the standardized variables, we have denoted standardized variables by Z. So, this is Z1 to Z5, where Zi is, as we have said, that Zi is nothing but xi minus xi bar by root Sii, right. This is true for I from 1 to 5, and this matrix is given by, it is a 5 by 5 symmetric matrix. So, this is given by, the variances are now actually the measure of correlation coefficient. So, diagonals are all 1, and then we have the off diagonals, the correlation coefficients. So, these are 577, 509, 387, 469, again we have 1, and then 599, 389, quite close values, 322, 1, and then 436, 426, 1 again in this position, 523, and the last element is of course 1. So, this is our sample variance covariance of the standardized variables or the correlation matrix of the original variables, right. And we calculate the eigenvalues from this matrix. So, the eigenvalues and corresponding orthonormal eigenvectors, that is all we need to get the sample principal components. So, corresponding orthonormalized eigenvectors of this matrix are, these are, well, these are lambda 1 hat is 2.857, lambda 2 hat is 5 of these, lambda 2 hat is of course what we said in the very beginning, that they are in decreasing order. So, that we are listing the values in this manner, 0.809, lambda 3 hat is 0.540, lambda 4 hat is 0.452, and lambda 5 hat is 0.343. I am getting the corresponding orthonormalized eigenvector are E1 hat, this is 0.464, 0.457, 0.470, 0.421, 0.421. This is my first eigenvector. The second eigenvector is given by 0.240, 0.509, 0.260, minus 0.526, minus 0.582, E3 hat, this is minus 0.612, 0.178, 0.335, 0.541, minus 0.435, E4 hat, the fourth one is 0.387, 0.206, minus 0.662, 0.472, minus 0.382, and the last one E5 hat is minus 0.451, 0.676, minus 0.4, minus 0.176, and minus, so this is 0.385. So, I have the first principal component using the standardized variables. So, because we have used the correlation coefficient matrix. So, we will mention it that using the standardized variables, the first two sample principal components are, well, the first one is y1 hat, and that is E1 hat transpose Z, and that is 0.464 Z1 directly from the first eigenvector 0.457 Z2, 0.470 Z3, 0.412 Z4 plus 0.421 Z5. And the second one y2 hat is from using the second eigenvector, that is E2 hat times transpose Z. This gives me 0.240 Z1 plus 0.509 Z2 plus 0.260 Z3 minus 0.526 Z4 minus 0.582 Z5. We are interested in calculating the proportion of variability explained by the sample principal components. We have stopped at two principal components because for us it is the easiest to manage two principal components. We can easily project the data in a two-dimensional plane and try and sort of interpret the data, but we must see before that how much of the total proportion of variability these two principal components are explaining. So, that this is nothing but given by the first two eigenvalues, sample eigenvalues. So, these components, these two components account for lambda 1 hat plus lambda 2 hat by sum of lambda I hat, that is 1 to 5, this into 100%, and this is nothing but 2.857 plus 809. You can see here that this is the trace of the matrix, sum of the eigenvalues of the R matrix. Now, trace of the matrix is nothing but sum of 1 up to p times. So, in case we are using the standardized variables, this summation lambda I hat, we can also write this as simply by lambda 1 hat plus lambda 2 hat by p, which is basically the dimensionality of the data, right. So, this is 2.857 plus 0.809 by 5 into 100%. So, this let us keep in bracket, this is equal to 73%. Okay. So, from real life data, it is about 73% of the total variability that the first two sample principal components are explaining. Now, if we look at the interpretation of these principal components, it is quite interesting to see. You can see that the first principal component is roughly, it is giving a weighted index to all the stocks, right. It is 0.464 with the first, 0.457 with Z2 in this way. So, this Y1 hat, this first principal component, can be thought of a sort of a market indicator, a market stock. It may tell you that it is basically giving you the weighted average of all the stock prices, right. The second one, if you see that it is grouping the first three and then it is grouping the last two. So, basically the first three stocks which are coming from the chemical companies, it is weighing these in one fashion, and then it is sort of segregating out from the other two, which are sort of together industry stocks of Exxon and Texaco. Okay. So, let us give this interpretation. Briefly, I will write this interpretation. The first stock, the first component, the first PC is roughly equally weighted sum. If you look at the weights, the eigenvalues there, these are almost equal, roughly equally weighted sum or sort of a market index or index of the 5 stocks. right. This component, this principal component, that is y1 hat, can be thought of, might be called a general stock market or just a market component, right. And the second principal component, the second PC, represents a contrast between the chemical stocks that is the first three allied chemicals, DuPont, and the third one is Union Carbide, and the oil stocks, the last two, that is Exxon and Texaco. Well, you may also go on calculating the other principal components. The third one will also come, the fourth one will come. Now, these may have positive, negative signs with any of these variables, and these may not be so easy to interpret, but of course, if you are not satisfied with 73% of total variability being explained, you can go to the third principal component, and together you can see that how much of the total variability the first three are explaining. Now, strictly speaking, when we are handling real life data, we should stop at 3-dimensional, otherwise the whole purpose is lost. We are trying to visualize the picture, the multidimensional data. If it goes beyond 3-dimensional, it really is of no use to us. Okay. So, and if we can give such nice interpretations, sort of it gives us some satisfaction that there is some nice interpretation to the principal components that we obtain. Okay. So, we end this example here, and next we take up situations where we start from the scratch, that is from the data, and I shall show you how you can use the SAS software to calculate the principal components with given data. Okay. And also, if you recall that initially we had talked about the various uses of principal component analysis, that is after the data dimension reduction, what all we can achieve through that, and I am going to explain you in detail on those aspects of the uses of principal component analysis. Okay. So, this is the principal component analysis. It's a part of multivariate exploratory data analysis technique. If you recall, we had told initially that the major uses of principal component analysis are its data dimension reduction. We start with a p-dimensional random vector, but ultimately we come to a k-dimensional principal components, k ideally 2 or at the most 3. And what does this reduction in data dimension do? Well, it helps us to project the multivariate data and visualize the various characteristics of the data. Now, once we project the multivariate data in the 2-dimensional or 3-dimensional plane, it serves some other purposes. We can see whether there is any outlier present in the data, hence we have multidimensional outlier detection. We have idea about the data cloud clusters, that is the grouping of the various of the data, right. Some of them will form one group, some other yet other will form another group in this way. And we can also do ranking of multidimensional data. How well we have the first principal component, on the basis of the first principal component, if you have now the multidimensional ranking of multidimensional data. So, this is our example where we start from the scratch and use the SAS software to calculate the principal components. It is a part of, it is a branch of multivariate exploratory data analysis, and if you recall the major uses of principal components, what we had mentioned in the very first session on this PCA, those were that data dimension reduction, where this is the crux of the backbone of the whole thing. We start with a p-dimensional data vector, but we come down to a k-dimensional principal components vector. k ideally is 2 or at the most 3, so that we can visualize the multidimensional data in a 2 or a 3 dimensional plane. Now, once we can project the data, so the reduction of data helps us in the projecting the data and visualize it. Once we are able to project the data, we can view certain other characteristics of the data, major of these being that we can see whether if there is any outlier present in the multidimensional data, or if the observations, if the variables are forming any groups. So, that is idea about data cloud clusters. We can also rank the multidimensional data. If you have a p dimensional data, say you have x p, right. So, how do you rank this? You have x 1 to x p. So, that is p such variables, and you have n observations on each of these variables. How do you rank such data? Now, what we do is we calculate the first principal component, say y 1, which is the first principal component, and for the first case, that is the first variable, we have the first group of observations, that is if we call it x 1, that is case, the first case is you have x 1, that is the first observation on all the variables x 1, x 2, x p. From here we get y 1, and then we go up to such n cases, that is we have total of n cases, case n, and say that I combine that in the nth vector from where we have y n. So, basically these are all y 1 to y n are basically the values of the first principal component, and then I can rank among these variables, and because these are now reduced to unidimensional data, and I can easily rank the unidimensional data and obtain a ranking of the multidimensional data. Similarly, checking for multivariate normality. So, by definition we have that x is going to follow a multi-normal distribution, multivariate normal distribution, say normal p mu sigma, if and only if every linear combination of x, that is L prime x, follows univariate normal. Now, we see that the principal component, again y, we have k such principal components y 1, y 2 to y k, and these are nothing but, if you recall, these are nothing but E 1 transpose x up to E k transpose x, right. These are the principal components. These are all linear combinations of x. So, this is our P transpose x matrix. So, we check for the univariate normality of each of these y 1, y 2 to y k, and if any one of these are not univariate normal, we have reasons to believe that this x data vector, it is not coming from a multivariate normal population. You also may have observation, a sample of size n. So, you have x 1, x 2 to x n from these multivariate normal population, and you have first principal component, you check it, the first principal component, what are the observations? You have y 1. So, say for y 1, the first one, you have these n observations, y 1 giving n, right. So, basically you now have a sample size, a sample of size n from univariate normal distribution. You have to check it, that whether it is actually coming from univariate normal distribution, which we all know there are certain ways, plots and certain other things from which you can check it, and then if it is satisfied, then you say that it is coming, the first principal component, that is a one linear combination is coming from the univariate normal distribution. Similarly, you go on checking up to the kth principal component, that is n observations, again a sample of size n from a univariate normal distribution, checking that, and if it is, if all these are satisfied, we can believe that x is coming from, these observations are coming from a multivariate normal population. If one of them is not satisfying the univariate normality, we may say that these may not come, this data x 1, x 2, x n may not come from the multivariate normal population. Now, the example that we do, the first one is, we have, this is the famous iris data published by Fisher, very very old data, 1936. It has been widely used for examples in other branches of multivariate analysis also, like discriminant analysis and cluster analysis. Now, what has been collected here is the data on the iris specimens. This is a type of a flower, and there are 3 species of this iris flower, the iris setosa, iris versicolor and iris virginica, and 4 characteristics on each of these 3 types. Data on these 4 characteristics are collected. So, this is just a snapshot of this 4-dimensional data, and you can see this is a 150 by 4 data matrix. So, in all we have 150 observation vectors. So, out of which how many are for this first species, how many for the second, that is we can see if it is there, fine, otherwise we have to just find it out from the data. Here we have only a part of the data. So, the first characteristic is the petal width, the second is petal length, the third sepal width, and the fourth is sepal length. ST, you can very well understand that ST stands for iris setosa. So, for this we are using ST. For iris versicolor we are using VS, and for iris virginica we are using VG. And these are the data, these are the length in millimeters of these 50. Okay, it gives that there are 50 specimens from each of the 3 species. So, that makes it 150, it is given here. Okay. So, these are the part of the data. Let us see what we can do with this data. Now, what are we going to do? It's easily, you can guess it, that if we can project this 4-dimensional data on a 2-dimensional plane and see that if there is any link of these with these measures, that is the measures of the characteristics and the type of the species. At least from this snapshot you can see only with the first characteristic, that is petal width, whenever it is iris setosa, you can see that it is okay, a small value, it's 2. So, it is about 2 millimeters. So, petal width is really small with respect to the other 2 species. But what happens to the other 3 when you consider the other 3 characteristics? Very readily you cannot say anything, and it is just a data in front of you, a 4-dimensional data. So, to get out something from this data, we try to project it in a 2-dimensional or at most a 3-dimensional plane. So, the next thing is the SAS code for calculating the principal component. So, this is how we have named these are comments anyway. So, these are put within this /* and we have stored this data and named it as iris. It is given in this editor itself. So, it is with card system that we have input the data, and these are the 4 characteristics, the petal width, petal length, sepal width and sepal length. So, we have entered the data, run it, and then we call proc princomp, that is the SAS subroutine for it, that is procedure princomp. We have data is iris, that is how we have named our data, and out file is print out. And we sort by the first principal component, that is we rank the data by the first principal component. We also plot the data, and we plot this, we obtain a 2-dimensional plot of principal component 1 by principal component 2. So, these are the number of observations, number of variables, that there are 4 characteristics. So, that is 4, and the mean of the different characteristics, that is x1, x2, x3 and x4, the 4 characteristics, these are the sample mean. So, that is the first one was, if you recall, it was petal width or petal length, that is petal width. This has this sample mean. Next is petal length, sepal width and sepal length, and similarly the sample standard deviation. This is the sample correlation matrix we have calculated, that so that it is for the standardized values, and then eigenvalues calculated from the correlation matrix. These are the 4 eigenvalues ordered. So, in the decreasing order, the first one being 2.91, then 0.91, 0.15 and 0.02. This is the difference, the successive difference, and this is the proportion of variability. So, this is what is important to us, the proportion of variability that each of these eigenvalues is explaining, and this is the cumulative part. So, that is this is the first, the variability explained by the first principal component. First two principal components explain 96% of the variability, and when I take the first three, well, almost the total variability is getting explained, because you see here it is 0.994. Okay. So, I think in this situation the first two principal components are good enough, because the two together are explaining 96% of the total variability. And these are the principal components, in the sense that we have the constants, that is the coefficients given to you. So, these are the values, the first principal component, these are the coefficient of this variable, and we have to calculate the principal, the case by case value of the principal components with the given value of these characteristics, right. These are the coefficients given for each case. And this is the scree plot. It gives you, tells you that the number of eigenvalues, that is the first eigenvalue, what is its value? It is close to 3, 2.9 something. The second one is 0.91. So, this is the value. The third one has this value, and the fourth one is this. Now, the scree plot, it comes down in the shape of an elbow. Like you see here, if you come here, this point may be called the elbow point of the scree plot. So, this is sort of the elbow point here, and then it flattens out, right. So, this elbow point tells out that we can stop at this point, at this number of eigenvalues, at these number of principal components. There is no reason to go beyond. Okay. Actually, in this case, even if we stop here, it is good enough. Okay. So, this is the significance of the scree plot. It actually plots the values of the eigenvalues, right, and tries to see that at which point you have the elbow point. This is just 4-dimensional, but you may have much higher dimensional data, and in that case it's sort of useful to us. And this is the 3-dimensional scatter plot. We look at the 3-dimensional scatter plot of the data. So, we have all the 3 axes here, principal component 1, 2 and 3, right. And we try to see that if we can see any grouping, any outlier. This is a sort of an outlier. This is the first one, ST, and these are VS and VG. So, you see VS and VG are sort of clubbed together, right, and ST, the first group, the first species, is forming a cloud of its own. These are totally mixed up. It is very difficult, but still you see that on this side you have some of the VGs which have separated out. Here on the lower part, some of the VS have separated out, and this mix, the middle portion is these VGs and VS are totally mixed up. Okay. So, let us go to the next plot, and this is the again a 3D scatter plot, but it is given from another orientation. Here it is sort of much clearer about, we can see clearly the 3 groups. The first one come nicely in this type of 3D plot. Okay. And you may say that some of these, like here one and here, mainly the third species, some of them are outliers. Okay. If we do it in the 2-dimensional plot, that is, we are only considering principal component 1 and principal component 2, these are the 2 axes. Here also the grouping comes quite nicely. The lowest one is giving you the first species, right. The red colored one is the second one, VG, and the third, that is the green colored, is giving you the third species, VS. Again we can see some data outliers in these situations, right. So, these are the principal components. For the case by case, you put the value of the characteristics, obtain the data and plot these here to get these plots. Okay. Our next example is about some financial variables. This is a principal component projection of profitability of banks data. What we have is a sort of a number of financial variables on the bank's balance sheet ratios, financial management ratios and profitability ratios. These are some of the very important characteristics of the on the performance of banks. Okay. So, these are the data basically we have, and these are the abbreviated forms of the data, and what we have is data on all those characteristics for some private sector and public sector banks of the Indian economy. Okay. This is again snapshot of the multidimensional data. This is huge data. We have looked into a number of financial variables for a number of banks. So, both P and N is quite high in this case, and this is a snapshot of that data. Now, what we do in this case is we separate out the private sector banks and we have calculated the principal components from the sample from the data that we have. So, we have first segregated the private sector banks and the public sector banks, and then calculated the sample covariance matrix or the correlation matrices for each of the two cases, and then we have done the grouping separately. Of course, you can do it in a same plot also, that is without segregating private sector and public sector banks. That is the purpose, basically it depends on the purpose, on your priority, what you are trying to see. So, here we are trying to see how the variability of the private sector banks among themselves, they are getting explained by the characteristics, and similarly how these characteristics are going to explain the variability present in the public sector banks. If it is for the whole banking system of the country, you will do it for the combined data, right. So, this is the first one is for the private sector banks, and we have plotted, we saw that the first two principal components were sort of good enough for us. The exact proportion of variability etc. are not stated here. The main thing is we are looking at this sort of groups and clusters here. However, the first two principal components served our purpose, and then we projected the data on a two-dimensional plane, and then we sort of try to see that based on the characteristics whether we could form groups of banks, that is performance of the banks based on the variability of the characteristics that are given. These can be said to be, they are more or less same, they fall in the same group. So, in this way we have some of the banks which are totally falling outside the clusters. So, they can be termed as the outlier, and some of them are coming in one group. So, we can say the performance, again it is performance solely on the variability present on those financial ratios that we are considering. So, based on that, these banks come under one group, these private sector banks come under one group, and so on and so forth. Okay. The second one is for the public sector banks. You can see that you have similar sort of grouping possibly for the public sector banks also. Here also we are projecting it on the two-dimensional plane. So, it means that we are satisfied with the variability explained by the first two principal components, and we see that here you can see the State Bank of Mysore is an outlier here, and the Indian Bank, probably for that data period the Indian Bank had a major setback. So, this is one outlier here. Otherwise, you can see the UBI and UCO Bank, they are in one group doing not too well at that time, and here we have one group of Allahabad Bank, Punjab and Sindh Bank, Overseas Bank, SBI and Bank of India, similarly are some other banks. Here we have a group of Canara, Dena, Bank of Baroda, Andhra Bank, okay, and again a small group here for the OBC and the Corporation Bank, and Vijaya Central Bank and one other is forming a group here, and these are mainly the SBI group, the SBI Saurashtra, and then we have SBI Indore and another one SBI, this is some other group is of the State Bank. So, this is about the public sector banks of India. The data period is probably not mentioned here. This is with again with respect to that data period. It's not mentioned. It is also an old data about maybe data of the 1990s, and these are the financial variables that we have here. So, number of them, these are the characteristics giving you the dimension of the data, and the observations, you have the number of banks, right. So, this exercise can be repeated for the whole banking industry of the Indian economy if you combine the private sector and public sector banks and then project the whole data. But for this type, we were mainly interested in the analysis where we were comparing the different sectors within themselves, and hence we obtained this sort of plots. So, this is how we can make some very nice practical application of principal component analysis, and with the help of this technique we can really do some intelligent analysis of the multidimensional data, which otherwise is just a group of haphazard data to us. We cannot do any ranking, we cannot do any projection of that data, we cannot make out any meaningful conclusion or interpretation of such data. It's just like a jungle of data in front of us, out of which you cannot make out anything. But if you can reduce the dimension of the data, that is the crux of it. If you can reduce the dimension to k equal to 2 or 3, then it is with the help of the projection of the data, you can not only see the different groups, you can also see if there is any outlier, and the ranking of data is also possible. Ranking of course makes sense if everywhere we are saying that it is ranking based on the first principal component. So, obviously, we are assuming that the first principal component is explaining about at least about 70% of the total variability. Otherwise, ranking on the first principal component does not make much sense, and of course, if that does not make much sense, then going to the second one also is not much helpful to us. So, in this way we can make some nice use of this technique of multivariate analysis.